All right, guys. So the next topic is local linear approximation. Local linear approximation and differentials. Approximation. Differentials. Okay, so suppose that y equals f of x is a differentiable function and suppose that x equals a is in domain of f. So our goal here is to approximate the value of f of x if x itself, if x is close to a. And to approximate this with if x is close to a with a straight line. Okay, so see, let's say we have a differentiable function and let's say we have some point x equals a in the domain. And we want to estimate or approximate the values of f of x if x is close to a with a straight line. So what is the benefit of approximating? Because when we go from exact value to approximation, where we are losing some information, right? So we need to really get some benefit in order to have a motivation for that. So what will be our motivation to approximate a function, a differential function with a straight line? So motivation is that straight line, well, is the easiest type of function, right? So we can, for example, for evaluation, let's say, for example, we have square root of something, right? Or e to some power, then we need calculator. But for straight lines, we don't need calculators. We can just plug the number, even manually, we can calculate it. So evaluation becomes easier when we work with straight lines. So that's one benefit. So benefits of replacing the function with a straight line. Straight lines are easy to work with for evaluation purposes. Or there's a differentiation, integration that you will see in the next course, etc. It's always easy to work with straight lines, okay? So we always prefer to have straight lines. Of course, we go from exact value to approximation. We lose some information there, but we gain some benefits as well. Okay. So what will be the best candidate for approximating f of x if x is close to a? So our candidates So one candidate is simplest one. So what about if I use the horizontal line y equals a? See, y equals a. Look at y equals a. If x is close to a, for example here, f of x will be close to f of a. So y equals f of a, I meant, sorry. Y equals f of a. If x is close to a, then f of x, we can say that f of x is close to f of a. Why is that true? Because f of x is assumed to be differentiable at x equals a. So this implies that f of x is a continuous at x equals a, and therefore this means that limit f of x as x approaches to a is equal to f of a. So what does that mean? That means if x gets closer and closer to a, if x is very close to a, then f of x will be very close to f of a. Therefore, f of a can be used as an approximation for f of x. Okay, so this one this is called approximation of f of x with a constant function. Let's look at an example. Let f of x equals root x, which is differentiable on 0, open interval 0 to infinity, and let a equals 4. Then f of, let's say, 4.1, which is root 4.1, can be approximated by f of, see, this is f of x, x close to a. So see, we have a fixed point. Let me show you here in the picture. We have a fixed point here, a equals 4. And then f of 4, which is 2. And then 4.1 is some point here. F of 4.1, which is root 4.1, can be approximated by f of 4, which is 2. Because these two values are close to each other, right? Approximated means we say one value is approximation for the other one if those two values are close to each other. So f of 4.1, which is this value here, is close to f of 4, which is 2. So we can say f of 4 is an approximation for f of 4.1. So then f of 4.1 can be approximated by f of 4, which is 2. according to or using the constant function approximation method. Okay, so this is the simplest type of approximation that we can have. But in practice, usually, well, this approximation is an approximation, but it's not good enough for us. We want to improve our approximation, meaning that we want to have smaller error, because each approximation always leads to some error, right? So we want to have a smaller error. We want to have a better approximation. So what should we do? So next, we want to improve the method above to derive a better approximation for f of x if x is close to a, i.e. an approximation with a smaller error. Okay, so there you are. This is the function. This is x equals a. Now, if you want to have, so f of a is simplest type of approximation, but if you want to have a better approximation, what would you use? See, this red line is close to the black curve, but can you consider another type of line which is closer to the black curve compared to this red line? So our candidate will be the tangent line at x equals a. The tangent line at x equals a has the property that, see, is closer to the original graph, the original curve, compared to the horizontal line, f of a. So this one is y equals f of a, but this blue line is the tangent line at x equals a. So according to the picture, which according to the figure above provides a better approximation for f of x compared to y equals f of a. So what is the equation of the tangent line at x equals a, which provides a rather good approximation for f of x? So equation of this tangent line What is it going to, what is the slope of this tangent line? The slope is f prime of a, right? Because it's tangent at x equals a, so the slope is f prime of a. And it passes through which point? So this point here, the point of tangency, basically is a and f of a, right? Because the graph is f of x. So if the x value on the curve is a, then the y value will be f of a. So the point of tangent is a and f of a, and the slope is f prime of a. So then the slope of the equation of the line will be y minus f of a equals f prime of a times x minus a. So if I take f of a to the other side, y equals f prime of a, or f of a plus f prime of a times x minus a. So we can conclude that f of x is almost equal to f of a plus f prime of a times x minus a. For x close to a. So this is the formula for local, it's called local linear approximation. Local linear approximation for f of x around or at or around x equals a. Okay, so the left hand side is f of x, right hand side is the equation of tangent line at x equals a, which means the equation of this blue line, which is an approximation for f of x graphically. If you want to justify it graphically, it's an approximation because the blue curve, the blue line is close to the original black curve. If two curves are close to each other, it means the y values are close. So one can be used as an approximation of the other one. So both, and the horizontal line y equals f of a and this also blue line tangent line, they are both approximations for f of x for x close to a, but the blue line provides a better approximation compared to the horizontal. It's a little bit more complicated instead of just a constant, because constant function, of course, the easiest type of function in the world. The blue line is not a constant function, but still is a straight line. So still is very simple. Not as simple as just a constant function, but still very simple because it's still just a straight line. Okay, so let's see an example. Use the local linear approximation method to estimate the value of root 4.1. So previously we said root 4.1 is almost 2 using just a constant function approximation. But this time we want to use local linear approximation to find an estimation for root 4.1. Okay, so what is our function here? See, because when we say local linear approximation method, so we need to have a function f of x, and we need to have a fixed value x equals a, and some x close to a. So we need to figure out each of these objects or quantities. So first, find out about the function f of x. So how can we find about the function? So here we have a square root of a number. So we just need to look at the form of the number that we have here. If you have sine of a number, for example, then f of x can be considered as sine x. If it's a cos of a number, then f of x can be considered as cos x. If it's, for example, e to some power, if you have a number in the form e to some power, then f of x can be considered as e to the x. Okay, if it's cube root some number, f of x could be considered cube root x. So just look at the form of a number, and based on that, make a guess for the form of f of x. So here is square root of a number, so f of x. So we choose f of x to be square the number, so we choose f of x to be f of x equals root x, square root x. Okay. And what about the value for a? So for the value, first find out about the function f of x, then make a guess for our a. So how can we make a guess, or based on what should we make a guess for a? Well, a is generally a number close to the x value that is given to us. So a must be close to the x value given, to the given x value. Here, x equals 4.1. X equals 4.1. And f of, and normally we must be able to compute f of a without calculator. Okay. So we have to choose a number which is close to 4.1. And f of that number must be, you normally compute it without calculator. So which numbers are close to 4.1? Many numbers are close to 4.1, like 4. I don't know, 11 or 4.09, right? But which of them, for which of them, f of that number, f of x is root x, can be computed without calculator. For example, f of root 4.11. Root 4.11, we cannot do it without calculator, or root 4.09, not without calculator. But which number close to 4.1, we can calculate root of it without calculator? 4 itself. Root 4, we can of course calculate without calculator, which is 2. So here, choose a cos 4 close to 4.1, and f of 4 is root 4, which is 2, can be computed without calculator. So that's it. So we can say that f of x is almost equal to f of a plus f prime of a times x minus a. And what do we know? We know that f of x is root x. X is 4.1. And a is 4. F prime of a will be 1 over 2 root 4. Because f prime of x is 1 over 2 root x. If f of x is root x, f prime of x will be 1 over 2 root x. So that one we can calculate, which is going to be 1 over 4. And yeah, we have everything. So root 4.1 almost equal to root 4. F of a is root 4 plus 1 over 4, which is f prime of a times x minus a times 4.1 minus 4. So that gives root 4.1 almost equal to 2 plus 1/2 times 0.1, which is 2 plus 1 over 0.1 is 1 over 10 times 1/2 is 1 over 20. So this is 41 over 20. So root 4.1 almost 41 over 20. And if you want to write this in decimals, so that's going to be, can multiply with 5, and then that's going to be 205 divided by 100. And 5 divided by 100, and this is 2.05. So this is an approximation for 4.1 is 2.05 is an approximation for root 4.1 using local linear approximation method. So one immediate advantage is that we could estimate, not calculate the exact value, but estimate root 4.1 without calculator. Now, that's just one immediate advantage. Like I said, for the topic of differentiation and integration, working with straight lines and in general polynomials are much easier, right? So for example, in Math 114, you will see that you can generalize this concept to write an exact value for a function. Right now, it's an approximation, but you can have an exact value if you generalize this to a series. Series means, it's generalized form of a polynomial. So a linear term plus a quadratic term plus a cubic term plus ... You can replace almost any differentiable function with a series of the form that is a generalized version of a polynomial. And working with polynomials are very easy. You can easily differentiate them, you can easily integrate them, right? So not only this concept is important, the generalization of it is also very important. And if we work with a generalization, we can have an exact value for a function rather than having just an approximation for the function. Okay, so let's look at the next example. So suppose that x is a small number close to 0. Find the linear approximation for the following functions. So let's say part A, sine x. So what will be the linear approximation for sine x if x is close to 0? So here, f of x is what? F of x is sine x, and x is close to 0. So what can I choose as my a? So choose a equals 0. Because remember, a is supposed to be close to x. X is close to 0. So a must be close to x. And also, f of a must be computed without calculator. And of course, f of 0, here in this case, sine 0, of course, it can be computed without calculator. Choose a equals 0. Because, you know, it's close to 0, as I mentioned here. And also, f of 0 can be sine 0 equals 0 can be computed without calculator. All right, so what can we say? We can say that f of x is almost equal to, we have the formula for local linear approximation. F of a plus f prime of a times x minus a. So f of x is almost equal to f of 0 plus f prime of 0 times x minus 0. Now, what is f prime of 0? So here, f of 0, we just said is sine 0, so it's 0. F prime of x, if remember, what is f of x? F of x is sine x. So f prime of x, derivative of sine x is cos x. So f prime of 0 will be cos 0, which is 1. So we can say that f of x, which is sine x, is almost equal to 0 plus 1 times x minus 0, which means x. 1 times x minus 0 means x, plus 0, still x. So what did we conclude? We concluded that sine x is almost equal to x itself for x close to 0. So for example, if they ask you to estimate sine 0.1, sine 0.1, we can also say almost equal to 0.1 itself, because 0.1 is close to 0. Okay, I can also show you in the graph why we are saying that. This is a very interesting phenomenon that, you know, the y equals x is a approximation for sine x. But see, the picture also suggests this. Look at the graph of sine x and look at the graph of y equals x. See, they're very close to each other. If they intersect at 0, but they're also very close to each other if x is close to 0. So y equals x is as an approximation for sine x if x is close to 0. So now for part B, so this was part A of the question. For part B, let's consider y equals e to the x. Again, for x close to 0. So this time again, choose a equals 0. Right, because f of 0 equals e to power 0 equals 1 can be computed without calculator. And what can we say about f of x? So we can say that f of x is almost equal to f of a plus f prime of a times x minus a. So what is f prime of a here? A is 0. And what is f prime of x here? F of x is e to the x. And f prime of x, therefore, is also e to the x. So f prime of 0 is equal to e to power 0, which is 1. And so we can see that f of x is almost equal to e to power 0. E to power 0 plus e to power 0 times x minus 0. So that is 1 plus x. So we can say that f of x is almost equal to 1 plus x for x close to 0. F of x, which is e to the x. E to the x is almost equal to 1 plus x for x close to 0. E to the x is almost equal to 1 plus x for x close to 0. For example, let's say e to power 0.1 is almost equal to 1 plus 0.1, which is 1.1, right? Using linear approximation. Linear approximation for e to the x. Okay. So let's look at the next example. Okay, show that 1 plus x to power k is almost equal to 1 plus kx for 0 for x close to 0, for x close to 0, and use this result to estimate the value of 1.001 to power 37. Okay, so here, what is f of x? Here, f of x is 1 plus x to power k. And x is close to 0, so we can choose a equals 0. Then what can we say? Then we can say that f of x is almost equal to f of a plus f prime of a times x minus a. And what is f prime of x here? So here, f of 0 is 1. F prime of x is k times 1 plus x to power k minus 1 by the power rule, right? 1 plus x to power k derivative is k times 1 plus x to power k minus 1. So f prime of 0 will be k. And so we can say that f of x, which is 1 plus x to power k, is almost equal to 1 plus k times x minus 0 which is 1 plus kx. So we can say 1 plus x to the power k is almost equal to 1 plus kx, which was the first part of the question. And the second part of the question, for second part, for estimating 1.001 to power 37. So here k is 37, x is 0.001. So then we can say that 1 plus x, 1 plus 0.001 to power 37 is almost equal to 1 plus 37 times 0.001. And this is 1.037. So this is an estimation for uh, 1.001 to power 37 using local linear approximation. Our next topic is about differentials, which is related to this linear approximation topic. I'll tell you the relation and the connection. Let me first tell you about the definition of differentials. So let y equals f of x be again a differentiable function.
Look, Les is here too. First, Farmer Tom and Les check the grass to see if it's ready to cut.
Define a differential of y denoted by dy as follows. So dy, we want to define it as f prime of x times dx. F prime of x times dx. So here, note that dy is a function of x and dx. Okay, so normally when we talk about functions, we have one independent variable and then one dependent variable. So once we determine the value of independent variable, then the dependent variable can be computed, right? So if I say, for example, x equals 0.1, then 1 plus x can be computed as 1.1. But here, it's a little bit different. We have two independent variables, x and dx. So dy is a function. Y originally was function of one variable x, but dy now it's a function of two variables. So two variables must be determined in order to determine the value of dy. What two variables? X and dx. So if I determine the value of x, of course, I need to know the function f of x, the formula for f of x, so that I can calculate f prime of x. But I also need to know the value of x and also dx. Once I know the value of x and dx, I can compute f prime of x times dx, and that will give me the value of dy. So for example, let's say let y equals 3x cubed plus 2x squared. Find dy if x is equal to 2 and dx is equal to, let's say, 0.1. Normally for dx, we use a small number normally. So I will explain why we usually use a small number. But it doesn't have to be a small number, because the function of two variables, x and dx, and any of these two variables, x and dx, can take any values. For example, in this case, I'm saying that let's assume x is 2 and dx is 0.1. find the value of dy. Of course, if you change the value of x or change the value of dx, of course, the value of dy will change as well. Now, dy will be how much? So dy is f prime of x dx. So what is f prime of x? So f of x equals 3x cubed plus 2x squared. So derivative of this function is 9x squared plus 4x. And then dy will be equal to, so add the values of x equals 2 at x equals 2 and dx equals 0.1 will be how much? Will be f prime of 2 times 0.1. How much is that going to be? So dy at x equals 2 and dx equals 0.1 will be equal to 9 times 4 plus 4 times 4 times dx, which is times 0.1. So 36 plus 16, 52 times 0.1. So that's going to be 5.2. So dy will be equal to 5.2. If x is 2 and dx is 0.1, and for this particular function. So here, like I said, I can change any of these as well. I can change the function, change the formula, or change the value of x, or change the value of dx, or change all of them. So let's look at another example. Let's say let y equals sine x. Find dy for, let's say, x equals pi and dx equals 0.2. So dy, again, see what is f of x here? So here, y equals f of x equals sine x. So dy is equal to f prime of x dx. So dy will be equal to cos x dx. So dy at x equals pi and dx equals 0.2. At x equals pi, dx equals 0.2. It will be how much? It will be cos pi times 0.2. Cos pi is minus 1, so the answer will be minus 0.2. That will be our answer. Now I want to tell you about the relation between differentials and linear approximation. The differentials. Differentials and linear approximation. So what was the formula for linear approximation? Let's remind ourselves. So we saw that f of x is almost equal to f of a plus f prime of a times x minus a. So that means f of x minus f of a will be almost equal to f prime of a times x minus a. Now, if I set, so consider y equals f of x, then dy will be how much? Dy will be f prime of x dx. Now, let's evaluate dy at x equals a and dx equals delta x, which is x minus a. Then what can we say? Then we can say that dy
The glass has to be pushed
will be equal to f prime of a
Tractor's head is helping.
times x minus a. dy at these values, at x equals a and dx equals delta x. But what is this? F prime of a times x minus a, according to this formula, is an approximation for f of x minus f of a, which is delta y. So let me call this formula 2 star. So by 2 star, f prime of a times x minus a is an approximation for f of x minus f of a, i.e. delta y. So what did we show? So what we were looking for the connection between differentials and local linear approximation. So what did we show? So we showed that dy, the differential, is an approximation for delta y if you set dx to be delta x and set x equals a to evaluate dy. Okay, so dy, which is in general is a function of two variables. But if you choose your two variables wisely, in the sense that you choose x to be a and dx to be delta x, then dy will give an approximation for delta y. It's not going to be exact value for delta y, but it's going to be an approximation for delta y. So let's look at an example of this. So use the differential dy. Use the differential dy to approximate delta y when x changes as indicated. X changes as indicated. So let's say y equals root 3x minus 1 from x equals 2 to x equals 2.03. So what did we show above? We showed that dy is approximation for delta y. And that's what the question asks us to do. It says, use differential dy to approximate delta y. Or we can write it also the other way. Delta y is can be approximated by dy. And what is dy? Dy is f prime of x dx. If the dx, by the way, has to be chosen as delta x. So what is a f prime of x here? So let me choose this function 3x minus 2. So what is f prime of x? F prime of x will be derivative of this function. U to power 1/2 derivative is 1/2. 1/2 times 3x minus 2 derivative times 1 over root 3x minus 2. So this is 3 over 2 root 3x minus 2. And then So then this will be f prime of 2 x is 2, the x is delta x. So then this will be f prime of 2 times delta x. Delta x means change in x. Change in x means 2.03 minus 2. -2.03 minus 2. And how much is that going to be? So this is going to be 3 over 2 times root 3 times 2 minus 2. That's f prime of 2. And then times 0.03. So the answer is 0.09 divided by 2. 6 minus 2 is 4. Root 4 is 2. So 0.09 over 4 will be our answer. Okay. Now let's look at the next example. Suppose that the side of a square is measured with a ruler to be 5 centimeter with a measurement error of at most 0.1 centimeter. Estimate the error in the computed area of the square. So what is the formula for area of the square here? See, we have let's say a square of, let's say, side length x. And what will be the area formula for the area? Area will be a of x will be equal to x squared, right? So what do we know? We know that delta x is at most at most 0.1 centimeter. So delta x, the error in measuring x is at most 0.1 centimeter. So we can say delta x is between, so we know delta x between minus 0.1 to 0.1. We want to know range for delta A. Or estimate range of delta A. Delta x means change in x, so the difference between the real side and the measured side is at most 0.1 centimeter. So delta x could be something between minus 0.1 to 0.1 centimeter. And we want to know the range of delta A is between which numbers? Is it also between, so if the error in measuring the side is 0.1, is the error in measuring area will be also 0.1, or is it going to be less or more? So that's what we want to find out. So how can we estimate delta A? So to estimate delta A, we can use dA, the differential, because we said that dy provides an approximation for delta y. Now what is dA? So here dA is equal to 2x dx. 2x dx. Because a is x squared. What is the formula that I use here? dy is equal to f prime of x dx. So here, instead of y, I have a, and my f of x is x squared. So f prime of x will be 2x. 2x dx will be dA. Now delta x, now if I set dx to be delta x, and x is how much? The measured side is 5 centimeter. So dA dA at 5, x equals 5, and dx equals delta x will be 2 times 5 times delta x, and that's 10 delta x. So what can I say? So you can say if delta x is between minus 0.1 to 0.1, then we can say that dA, which is 10 delta x, then 10 delta x will be between minus 1 to 1. So that means dA will be between minus 1 to 1. So estimate in error in computing area will be 1 centimeter. So that's dA is an approximation for delta A, which is error in computing the area. So it's, delta A the error in approximating error in computing the area is estimated to be at most. So when we say between minus 1 to 1 means in magnitude is at most 1. To be at most 1 centimeter squared, right? Because the unit for area is centimeter squared. So the magnitude is at most 1. Could be between minus 1 and 1 means it could be minus 0.1. In that case, the error will be 0.1 centimeter squared. But in the worst case, it's going to be 1. So 1 centimeter squared in the worst case is going to be the estimated error in computing the area. So we calculated the range for dA between minus 1 to 1, but dA is an approximation for delta A, which is, and delta A is the error in approximating the area. So the estimation in computing delta A is at most 1 centimeter squared. So if we make at most 0.1 centimeter error in measuring the length, and if the measured length of the side of square is 5 centimeter, then under these circumstances, the error in area will be at most 1 centimeter squared. But that's only under this condition. If, for example, for a different measured length, if, for example, the measured length is 6 centimeter, then the measured error in computing area will be, of course, different. Okay, guys, so this is about differentials and how we can use them to use approximation. Okay, thank you guys, and see you next time.